inverse trigonometric function derivatives. Goals here, know the derivative of the arcsine function and know the derivative of the arccosine function. We'll focus on the arcsine first, and first thing you need to do is recall that the arcsine is the inverse of the sine function. And in order to facilitate the one-to-one requirement that's needed for an inverse to exist, because if you look at that sine function, it fails that horizontal line test, doesn't have an inverse function as it originally stands, you have to restrict the domain of the sine function to negative pi over 2 to pi over 2. And in that way, that little bit, when you graph that, it passes the horizontal line test, and then the inverse, the arcsine graph, will become this. So you get this negative 1 to 1 on the x-axis now, because you're flipping the domain and range when you make the inverse, and you get this little graph that looks something like this. And the thing to note here is that the domain of the arcsine is negative 1 to 1. And that's going to come back when we start looking at the derivative result. So how do we find the derivative then of the arcsine? Well, first thing we're going to do is define y as the arcsine of x. And we use the other notation for inverse trig functions there. And what that really means, y equals arcsine of x, is that the sine of y is equal to x. This is another property of your inverse functions for trig, and something to keep in mind. So why am I making this switch? Well, ultimately, I want dy dx. I want dy dx from here. But I don't know anything about the arcsine really in terms of how to get to that dy dx. So what we're going to do is kind of take a roundabout, maybe the scenic route, and we're going to have the sine of y equals x. And by having that, I know the derivative of the sine. So what I'm going to use then is some implicit differentiation on that sine of y equals x. And on the left side, what we're going to get is the cosine of y. And since we're deriving with respect to x, we think of that y as being some unknown function of x. So using the chain rule, we got to take the derivative of y and multiply by the cosine of y result. So we get this dy dx. It's the derivative of y. And then tack that on. And over on the right side, you just get 1. So now we got the derivative of y with respect to x is equal to 1 over the cosine of y. And this technically is the derivative of our arcsine. We're looking for the derivative of y, which is equal to the arcsine. But the problem here is that I have y equals arcsine of x up above, and my derivative is in terms of y. That's not going to work in the grand scheme of things, applications. So I need to get this cosine of y adjusted to be in terms of x. So how are we going to do that? Well, this is where the sine of y equaling x will come in. So I'm going to create a triangle here, a little right triangle. And the angle in sine of y equals x is y. So I'm just going to put that into this corner. You could put it in the other one, but I'm just going to put it down here in the bottom left corner. And when the sine of y equals x, using the opposite over hypotenuse idea of what the sine is defined as in these right triangles, we would have x being the opposite of that angle, and 1 would be the hypotenuse. And if you use the Pythagorean theorem, you get the adjacent is the square root of 1 minus x squared. So now I can think about, okay, well, what's the cosine of y in this triangle that I've created? Y is still the angle, and the cosine is adjacent over hypotenuse, or that square root of 1 minus x squared over 1. And that then can be taken over here, and I get my dy dx, the derivative of the arcsine, is 1 over the square root of 1 minus x squared. So just using that right triangle trick, we've had some, a whole lot of things going on in this, using the knowledge of what the inverse means, using the implicit differentiation concept, which has the chain rule kind of built into it in a sense. That's why we multiply by that dy dx. And then we have to use, everything else we know about trigonometry in a sense in order to get to this answer. So it's a really good exercise. And therefore then, putting this all together in one line, the thing that's really going to be important to remember here is that d dx of the arcsine of x is equal to 1 over the square root of 1 minus x squared. And domain here, for the derivatives, your domain really can't go beyond what the original function is defined at. And if we look at the original function, negative 1 to 1, inclusive. But because negative 1 and 1 will make a 0 in the denominator, we go ahead and kick those out. And for the derivative of the arcsine, we just have a domain of negative 1 to 1, not including the endpoints. Okay, so let's go ahead and take a look at the arccosine. And this is going to be a similar process to what we did for the arc sine. Very similar, in fact. And again, just recall here, the arccosine function is the inverse of the cosine. Also had to restrict the domain in order to make it 1 to 1 so that we could get the inverse. And for the cosine, we restrict it to 0 to pi because it's a different looking graph. And we restrict it to a different interval to get that 1 to 1 nature. And if we go ahead and sketch this out, we still have negative 1 to 1 on our inverse domain. And then we'll have 0 to pi. And the graph looks something like that. And the domain of the arccosine, the inverse cosine function, is that negative 1 to 1 again. So, as I said, we're going to use a similar approach as we did with the arcsine development to find the derivative of the arccosine. And that means we'll start out by letting y equal the arccosine of x. And this implies that the cosine of y will equal x. And then again, we're using the implicit differentiation approach. So we'll have this cosine of y equaling x being derived with respect to x. And the cosine derivative is negative sine, so I'm negative sine of y, and then times that dy dx. And then this will equal 1. Then solving for dy dx, the actual derivative of the arccosine in this case, we get negative 1 over the sine of y. And we still have the same problem here as we had on the arc sine development. My dy dx is not in terms of x, which is what I want. So I'm going to draw a triangle again. And you got to keep in mind in this triangle, it's going to be a little bit different because of what we started with here with our cosine of y equaling x instead of sine of y equaling x. So things will shift around a little. But I am going to keep the angle in this corner. The adjacent now in this case becomes x. Hypotenuse is still 1. And if you use Pythagorean theorem, you could find the opposite as being this square root of 1 minus x squared. So what that tells me then, looking for the sine of y, is that it's going to be the opposite over the hypotenuse, or just square root of 1 minus x squared over 1. So it ends up being the same thing. The only real difference here, as you come over and complete this, is that instead of being a positive 1 over the square root of 1 minus x squared, as we saw for the arc sine derivative, we're going to get a negative 1 over the square root of 1 minus x squared for the arc cosine derivative. And putting that all down here, gave myself way more space than I needed, but maybe you write big. So we got this d dx of our arc cosine of x. is going to be equal to the negative 1 over the square root of 1 minus x squared. And again, the domain for the original arccosine was negative 1 to 1 inclusive, but because the endpoints will make zeros in the denominator of our derivative, we kick that out for the domain of the derivative function. All right, so one final note. The derivatives of the other inverse trigonometric functions can be found using a similar technique, using this implicit differentiation and triangle trig. So, if you want to develop the arctangent, arccotangent, etc., use a very similar technique here. So, at any rate, thank you for watching, and I hope this gives you a good foundation on those concepts.